Hi students. So today we are going to begin optimization tutorial 13b, and today we are going to look at the gradient descent directions and some of the properties about these directions specifically for the steepest descent method. I am Dr. Ganguly. Now we of course know that the steepest descent method has the form that dk is minus ck, and typically when you are moving in the design space in any direct search method, the algorithm has the form xk plus 1 equals xk plus alpha k dk. And what happens in the steepest descent method is that the search direction is simply the negative of the gradient vector. So we are defining the gradient vector by the notation c. Now today we are going to look at some of the properties of these search directions. We are going to look at whether the line search criteria is satisfied, and also we are going to further validate the fact that these particular search directions are going to be normal by looking at the angles between the search directions. Also, we are going to do this problem for quadratic functions so that it's relatively simple as far as 1D search is concerned, and I'm going to give you Python code for this problem. Now, of course, I will suggest that you review lecture 13 on steepest descent method if you get time, maybe after looking at this particular tutorial. Let us look at the mathematical definition as to what would happen if the search directions are normal. So what would happen is that dk dot dk plus 1 would be equal to 0. And of course, you know dk is the search direction at point k. Now the line search criteria would require that ck plus 1 dot dk will be 0. Of course, what would happen is that if you calculate this on the computer, these should be very small numbers. They will not be 0 because there is truncation present on computers. Let us formulate a problem and then check out these particular properties. So we are going to write a Python program for the steepest descent method, and we are going to use this program to demonstrate that the search directions dk and dk minus 1 are orthogonal, which is essentially a different way of saying that these are normal or at 90 degrees. And we will also try to prove the line search criteria. This should of course be satisfied. And we are going to look at the function fx is x1 square plus 2x2 square. We are going to start with the value 1 minus 1. So let's try to do this problem. Now before we do that, you should remember that if we have the function in a quadratic form, so we have a function like half xtax minus btx, then we can find the one-dimensional step size as alpha k is ckt ck ckt ack, where of course t stands for the transpose. So this is something to keep in mind. So of course you know that this particular value is a scalar. It can be obtained very simply, and we can use it in the calculation instead of the numerical 1D search. Now I can write f of x as x1 square plus 2x2 square, which is going to be half xt into this matrix, the A matrix, into x here. And you also know that for a quadratic function, quadratic form, this A matrix is nothing but the Hessian matrix corresponding to A. So that's something which we are going to use in this particular tutorial. Now if you are not familiar with quadratic forms, take a look at tutorial 2 for a revision of that particular subject. Let's now quickly write the Python functions. So essentially our function is very simple, x1 square plus 2x2 square. So the corresponding Python function is going to return x1 square plus 2x2 square. Now of course remember Python starts from 0. So instead of 1 and 2 as the subscript, I have to use 0 and 1. Now the next function returns the gradient vector which we require for the steepest descent method. So the gradient of this function is 2x1 and 4x2, and so I can return this particular vector here, and that's going to give me the gradient at any point x. Now we can use the definition of the scalar product or the dot product of two vectors to essentially get the value theta which is there between these two vectors. For example, if we have vectors u and v, the dot product is defined as norm of u into norm of v into cos theta. So I can write cos theta in terms of this simple expression in red. Now if we want to code this in Python, we can define a function. We can call this function theta, and it can take two vectors, let us say d and d old, and return the value of theta. So what I do is I first simply code in this formula here. So I write cos theta as the dot product of d and d old, these are the two vectors coming in, divided by the norm of these two vectors. So essentially d and d old are going to be the two search directions. Now what's going to happen is that I'm going to get cos theta from here. So I need to take arc cos to essentially get theta, but that also is going to give me the value in radians. So I need to then convert that to degrees. So essentially I need to essentially call the math library here also. So not only I have to call numpy, which is required in all these calculations, that is np, but I also need to call math, and these are required in the main function. So let's write the main program. So of course we know our function is given in this form here. So first I have to import numpy, then I have to import math. I have the starting design from 1 minus 1, and I also have the A matrix for the quadratic form as 2004, which I have coded in here. I fix a tolerance value as 0.401. This is going to help me to converge as far as the gradient vector is concerned, and also a max value which I am going to use in the for loop. And then what's going to happen is that I'm going to write a function called steepest, which is going to take the initial point x0, the tolerance small number, the max value of 1000, the A matrix, and it's going to return me x star, which is the optimal value of x, and k, which is the number of rounds it took to converge for the for loop. Let us take a look at the steepest descent function. Now I have slightly modified the function to also print out some of the values we are interested in. So this function essentially sets x as x0 to start off, and again it basically has a for loop here going for I in range max. So essentially we are going to go through the for loop, and we are going to break out if the norm of the gradient vector becomes below tolerance. So that's the breakout condition. So now here of course what we do is that we get c as the gradient vector, and then we set d as minus c. So that's the search direction. Now what we do is that when I becomes greater than 0, I essentially have access to both the current value and the previous value. Then I start calculating the dot products here. So I'm directly printing out the dot product, for example, of d and d old, and also I'm printing out the theta value which is there between d and d old, and finally I'm printing out the dot product which will tell me if the line search criteria is satisfied. That is the dot product between c and d old. So essentially the d old is dk plus 1, and then the c d old is ck plus 1 dk. Now you can think of this as dk into dk plus 1, or you can think of this as dk minus 1 into dk, and so on. So essentially this is how the function is going to work, and what we are going to do is that we are going to calculate the step size, and then we are going to print out the value of alpha here, and finally I'm going to update the search direction as x is x plus alpha into d. I also save this value of d and c in this particular vectors d old and c old because I am using this here. And finally I break out of this loop and I return x and I, which are going to be the optimal point and the number of rounds it took for the problem to converge inside the for loop. Now let us print out all these and see. So you can see here I've printed these out, and you see here I start from the point x is 1 minus 1, and each time we take a particular step size, and then we are moving forward and trying to solve this problem. And each time you see that the dk plus 1 dot dk, it's almost 0, and ck plus 1 dot dk is also 0. So these are all 0. If I printed them out in terms of numbers, they come out to e to the power minus 15, minus 14, something like that. So I have rounded them off to 0. And also we are seeing that the theta value is 90 degrees. So that further certifies the fact that dk and dk plus 1 is normal. So this is a particular property of the steepest descent method. So we continue with this. So iteration k is 4 to 6. You keep seeing this particular value satisfied. Both the fact that the directions are normal and also the fact that the line search criteria is satisfied. Finally, this converges to these small numbers here. Of course, you know for this particular problem, the optimal value is simply going to be 0 for both these points x1 and x2. So let's now do one more question, and this question essentially asks you to plot the search direction in the steepest descent method using Python and to see the trajectory of how these points, these directions change as the iterations progress. Again, we are going to use the same function, that is x1 square plus 2x2 square, and we are going to start from two different points. So the first point is going to be 1 minus 1 and the second point is 0.005 and minus 0.005. So you are going to get a good picture as to how this particular method works, and this is something which actually is possible in Python because it has a lot of power in terms of plotting functions and so on. So we are going to use this main program here, which I have slightly modified from before. So now we are not going to bother anymore about those particular dot products. For example, dk plus 1, dk is 0 and so on. So I have removed the math here, import math command, and now I'm going to import numpy. And also I am going to import a very important library known as matplotlib.pyplot as plt. So this is going to help me to do a lot of plotting of the different figures. Again, we start from the same point. X0 is 1 minus 1 and the A matrix of course is 2004. We have a small number for tolerance. We have max at 1000. And this time I'm not going to return the optimal point and so on. I'm going to return the history of all the x values and the history of all the d values. Remember, d is the search direction. So these two lists I'm going to get are going to give me the list of the history of the points and also the search direction. And then I'm going to define one more function which is going to help me to plot this time history of the different points and the search directions. So let us look at these two functions. So I have again modified the steepest descent function slightly. So again, this is the function here. And this time I include these two lists which I start off as simply lists which have nothing. And then I have the for loop here. I start with c is grad f. So I put the gradient into the c vector. I put d is minus c. I calculate the search direction for the quadratic. And I print out the value of alpha, the step size, and x. And now what I do is I actually use this particular command, the append command, to add to the list the current d, and also in the x list I add the current x. So I have two lists here, a d list and an x list, in which I am keeping track of the various values of the search direction d and the various values of the x vector here. And of course then I keep changing the x vector each time based on whatever alpha and d I have calculated, and I keep going through this for loop until I converge. And convergence is given by the fact that the norm of the gradient vector has become lower than tolerance. Remember, tolerance I am giving as 0.401. That's a small number. And finally I return the x list, which is going to contain all the points, all the x points here, and then I'm also going to return the d list, which is the point of all the search directions. Let us define a function for plotting. So again, the plotting function essentially takes the x history and the d history or the list values from the main program, and then it works with that. So the first thing we need to do is that we need to convert these lists into numpy vectors, which we do here, and then I create a bunch of values for x and y within the domain in which I think this particular problem is going to be. Then I create a grid and I calculate the value of the function x square plus 2xy square, and then I use the contour plot to essentially plot this particular function. Now beside this function, I am also going to plot all the different search direction as lines, and these are essentially going to come out as what are known as quiver plot. So these are essentially lines which are going to tell me exactly the directions of these particular d vectors. So these are going to be actually vectors, so you can see that very soon. So that's going to come out very well. And then of course we plot the title, steepest descent search direction, we label x and y, and then we have to put plot show to show this. Remember, again, plt is coming as a saved form of the matplotlib whole command. So let us see the convergence which we have given here. So starting from point -1, we essentially converge like that to something which is close to 0, 0. Let us now see what our plotting function gives us. So this is what we get. So we are starting from this point 1, -1, and this is the search direction. And we are going to move a certain amount here based on the one-dimensional search. Then the next direction is this one, so we move in this direction. We move a certain amount here, and then we go in this direction, and so on. So of course you can now visually see also that each of these search direction is normal. They are at 90°, which we have proved previously using the theoretical dot products and the angles and so on. Now it would be interesting to see how things would perform in this region, because it's getting kind of cluttered and obfuscated because of the lot of iterations taking place in this small region. So I'm going to take a particular sample point from the previous runs and going to use that. So that particular point was 0.005 minus 0.005. So I take that as the starting point, and I once again run this main program. So again, remember, in this main program I'm calling steepest, and I am also calling this function which is the plot contour with directions function. So here I am starting from 0.005 minus 0.005. So one of the things which I have done is I have changed this particular bounds as far as the lane space is concerned. So the x vals and the y vals are taken from this bound here. Now I lowered this bound so that the graph we are going to see soon is going to fit in properly in this particular situation. Let us again look at the convergence. So again, the convergence now is quicker, but of course, you know, steepest descent, because of that zigzagging, it keeps moving around the optimal point in that manner. So it is going all the time in that 90-degree situation. It's very close to the minimum, but it's not able to get there. This is some problem which we of course know happens in the steepest descent method. This is solved to a large extent by conjugate gradient method, Newton method, and so on. So again, we see here in this case that we are starting from this point 0.005 and minus 0.005, and we have this search direction. We move in that direction. After a point, we change this to here because we have the step size and so on. So we are going to continue like this at 90 degrees, and we are going to go on and on till we converge. So this of course lets us see the search directions very well. So of course many of you are probably familiar with MATLAB. You can do this in MATLAB also, but one of the things about Python is that you can not only do a lot of number crunching in Python, but you can also do a lot of plotting, making figures and so on also. So that's something to keep in mind. So let us summarize all the things we learned in optimization tutorial 13b. So in this tutorial we saw that the steepest descent directions are normal, they are at 90°, the line search criteria is satisfied, and we also looked at Python code and we learned about two new libraries such as the math library and the matplotlib. Now of course we know the general search method xk plus 1 is xk plus alpha k dk, alpha k being the 1D search, dk being the search direction. Steepest descent search direction is negative ck, and while this is a very good search direction, very simple search direction, it has the problem of all these search directions being normal, and that actually creates a problem for this method, because at first the method does very well, but later as it gets closer to the optimal point, it actually starts doing very badly. So some of that is going to be fixed by the Newton type of method, which we are going to consider sometime. And so remember always that steepest descent has this particular criteria, that is dk dot dk plus 1 is 0. And also the line search criteria is something which you can check out in many different algorithms out there. Sometimes this criteria is actually used to figure out if the one-dimensional search has converged or not. So we can say that ck plus 1 dot ck dot dk, if it becomes less than some small number epsilon, say tolerance, then we can say the 1D search has converged. So that's something which is also done every now and then. So again, make it a point to look at optimization lecture 13 for the steepest descent method, and also look at the tutorial 13a before you look at 13b, or in case you have not yet looked at 13a, then make it a point to do that.